Thank you very much. So first of all, it's my great pleasure to give a series of lectures at this conference, and I'd like to thank the organizers for inviting me to give talks. And in this series of lectures, I will speak about tensor ideas of the right bound in the category of finitely generated modules over a commutative Neperian ring. So, and also I will speak about Balmer spectrum, its Balmer spectrum. And this, everything in this series of talks is based on joint work with my PhD student, Hiroki Matsui, who is here. Okay, so let me give a background first. So this series of talks consists of 4 sections, and in section 1, I will speak about tensor triangulated. And their Balmer spectrum. So I will mainly introduce some work on Balmer. So I will speak about general theory on tensor triangulated categories. And from section 2, we will focus on the right bound derived category of commutative rings. So, and actually in section 2, we will consider compactly or co-compactly generated fixed tensor ideals of E minus small order. So R is a commutative Neperian ring. Model denotes the category of finitely generated modules over R, and this consists of complexes of R modules whose homology bounded above. So, and in this section, I will give a complete classification of compactly generated fixed tensor ideas and co-compactly generated ones. And at the end, we will see that these 2 notions, I mean, compact generation and co-compact generation, equivalent. So we will call them just as simply compact fixed tensor ideas. Okay, so this is the content of section 2. And in section 3, we will study Balmer spectrum of V minus 0 and some classification. Of big tensor ideas. Okay. So actually, in this section, we will introduce the notion of a tame fixed tensor ideal and compare tame fixed tensor ideals with compact or radical fixed tensor ideals. And also, we will study the topological properties of the Balmer spectrum of this derived category. And if time permits, we will enter section 4 to study the case of discrete variation rings. Okay. So actually, in fact, in the Artinian case, I mean, if the ring, our commutative ring is Artinian, everything is clear. So we will see this. So if R is a commutative Artinian ring, we will get the complete classification of all thickness ideas and compact, tame, and radical. So everything, we know everything about them in the Artinian case. So the first non-trivial case should be the case of discrete variation rings. So I will talk about it, but indeed, even in the case of discrete variation rings, the Varma spectrum of B minus small mod R is rather complicated. Okay. So this is the plan of this series of talks. So now let's enter section 1. Okay. So as I said before, in this section I will speak about, in general, tensor triangle categories. But as to what I speak in this section, please keep in mind just that I'm just an amateur. So I mean, I am not an expert. I'm just a purely commutative algebras. So I'm not so familiar with this general theory. And actually, I think some of you much more familiar with them. So, but if I say something wrong, please point it out. Okay, so first, let me remind you of the definition. Now, tensor triangle category. So a tensor triangulated category consists of three things. So P and tensor and 1. Okay, where T is, so this is just a triangulated category. Triangulated. P is a triangulated category. Equipped with symmetric tensor product. I mean, symmetric monoidal structure and unit 1. And we will also assume that these two structures, I mean, triangulated structure and symmetric monoidal structure, are compatible. So this is the definition, and let me give several examples of a tensor triangulated category. So yes. So first, so if X is a scheme, the derived category of perfect complexes with X is a tensor triangulated category with tensor product X. This. And the unit is the structure sheaf. This is a tensor triangulated category. And if we restrict to the affine case, we also know that the bounded homotopy category of projective arbiters, so R is now a connected ring. So KB project R is also a tensor triangulated category with usual tensor product over R, and unit is also R. Okay. So this is the tensor triangulated category, and if K is a field and G is a finite group, well, I think group scheme also, then the stable category of KG is a tensor triangle category with tensor product over K and the unit K. Okay. And the bounded derived category, BB mod KG, also a tensor triangle category. Okay. And finally, the final one will play the main role in this talk, in these talks. I mean, D minus small mod R and usual L tensor over R, where R is a commutative. Anything I'm waiting? Okay. So this white bounded derived category also has a structure of a tensor triangle category. Okay. And note that all of these are essentially small. And oh yes. Yeah, so these are essentially small tensor triangle categories. And so next we recall the definition of a thick tensor ideal, so thick tensor ideal, and Balmer spectrum. So let T be an essentially small tensor triangulated category. Then, first, a thick subcategory I of T is called tensor ideal. But in these talks, I simply call an ideal if the following condition is satisfied. So if A is in T and X is in I, then A tensor X is in I. So it's an analog of an ideal of a commutative or a ring. And next, an ideal, thick tensor ideal, I of T is called radical if it is equal to the radical here. So the radical of I denotes the Pearson category of T consisting of all objects A in T such that some positive integer n for the tensor product of A is in I. And this is also an idea of P, and it is called radical if these two are equal. So in general, this always contains I, but if the equality holds, then I is called radical. So, and this is also an analog of the radical idea in the commutative. Okay. And a proper idea P of P is called prime if x tensor y being in P implies x is in P or y is in P. So if this condition is satisfied, P is called a prime ideal. Of course, this is also analog of a prime idea of commutative. Yes. And so now we can define the Balmer spectrum. The Balmer spectrum of P is just a set of prime ideas. So it is denoted by SPC. Which consists of prime ideas of T. Okay. This is an analog of usual prime spectrum. So if R is a commutative ring, the prime, so this is an analog of spec of R, so which consists of prime ideas of R. And finally, we also define the Balmer support of an object E. So the Balmer support of x in P is, I denote this by SPP of x because I will use SUPP to denote another thing. So I use this notation. So this is the set of prime ideas P of T such that x does not belong to P. So this is the Balmer support. And this is an analog of, I think, V of x. So if x is an element in a commutative ring R, V of x is defined to be the set of prime ideas P of R. That contain x. So this is an analog of this, actually. So note that the containment is opposite. So the condition here is that x is not in P, but usual V of x in commutative ring, the condition is x is in P. And we also put Ux to be the complement of Varma support. Namely, this is the set of prime ideas P of T, such that Px is in P. This is an analog of D of X. So the set of prime ideas of commutative ring R contain that does not contain X. So, so in fact, and spec of R, so spec of R has a topology, so-called Zariski topology. And similar to this, the Varma spectrum also has a structure of a topological space. So let me explain this together with some other results, which will be used later. So first, as I said now, SPCT, so the Varma spectrum of P is a topological space with open basis Ux, where X runs through all objects in T. So Varma spectrum also is always a topological space. And similarly, many similar results to ideas in commutative ring are satisfied. So first, every proper ideal of T is contained in the maximal ideal. And all maximal ideals are prime. So any maximal ideal is a prime ideal. And also every prime ideal contains a minimal one, minimal prime. So all of these corresponding to all of these, so the statements in commutative rings corresponding to all of these are very, very basic results. And also for each prime ideal P of T, the closure of this one-point set is equal to the set of prime ideals Q of T, which is contained in P. So this is a closure. In this topology. also this is an irreducible closed subset. So this corresponds to the fact that in a commutative ring, each one-point set, the closure of each one-point set is equal to V of P, which consists of prime ideas Q of R, which contains P. This. Again, the inclusion is opposite here. And conversely, any non-empty, irreducible, closed subset is of this form. And dually, each ux is a quasi-compact. Ux is a quasi-compact open subset. So this corresponds to the fact that d of x, so d of x, so this d of x is quasi-compact. And conversely, any quasi-compact open subset has this form. And finally, we will also need this fact. So for each ideal I, P, so this is an ideal, the radical of I is equal to the intersection of prime ideals P, which contains I. Okay. So also the corresponding result in commutative ring is holds true. So there are many results about ideals of a tensor triangulated category similar to ideals in a commutative ring. Okay, so next. Okay, so now let me introduce some notation. So for X, for a subcategory X, full subcategory X of T, and a subset S of the Balmer spectrum, we set SPPX. So the support, Barman support of X, will be the union of Barman support of object X in X. And we denote by SPP inverse S to be the first category of P consisting of all objects X whose Barman supports are contained in S. Okay. So then, the programmers prove the following theorem. So this is the Barmer, 2005. So there is a one-to-one correspondence between the set of radical ideals, radical fixed ideals of P and the set of Thomason subsets of the Barmer spectrum. There is such a one-to-one correspondence between these two sets. And these maps are explicitly given by taking support and supporting Barmer support and Barmer support. So from here to here, SPP, from here to here, SPP inverse. And so what is the Thomason subset? So a Thomason subset is defined for any topological space. So here, a subset A of a topological space X is called Thomason if A has the following form. So A is the union of some BI where BI is a subset of X whose complement, so I mean X minus BI, is quasi-compact open subset. Such a subset of the topological space is called Thomason. So in particular, so since this complement is open, so BI, the original BI is closed. So this is A is a union of closed subsets. So A is a specialization closed. So any Thomason subset is specialization closed. Okay. And moreover, Barmer mentioned that the following statement holds true. So this is stated in his paper, in his two papers, published in 2005 and 2010. So the first statement says that if X is a scheme, I mean quasi-compact, quasi-separated scheme, if X is a scheme, then the Balmer spectrum of the derived category of perfect complexes is isomorphic to X as ring spaces. So this isomorphism is as ring spaces. So in particular, any scheme, any quasi-compact, quasi-separated scheme can be reconstructed from its derived category. And second, corresponding result for group, so finite groups, also to, so he also mentioned the following. So if K is a field, and G is a finite group, then the Balmer spectrum of the bounded derived category of KG is isomorphic to the homogeneous prime spectrum. So homogeneous prime spectrum of the homology ring. And also this isomorphism deduces, so this isomorphism yields the following isomorphism. So the SP is in the Balmer spectrum of the stable category, mod bar KG, is also isomorphic to proj of the cohomology ring. So now let me introduce one more notation. So let P be again. So now we go back to the general theory. So let P be a general, essentially small tensor triangle category. Tensor triangularity. Then Balmer's construct a continuous map rho T dot from the Balmer spectrum of T to the homogeneous prime spectrum of some certain ring, commutative, graded commutative ring. Here, RP this is a graded commutative ring. Hom P1 shifted line. This is a graded commutative. So precisely speaking, this is a direct sum of offsets from one, so from the unit 1 to the unit shifted by n. Okay. So he constructed such a continuous map. And also he proved that so the isomorphisms here, so this isomorphism and this isomorphism are obtained by this map, rho t dot. So I should write here. So the isomorphisms in theorem 1.6 are given by rho t dot. So in these two cases, so if T is the derived category of perfect complexes or the bounded derived category of KG, this map rho t dot is actually a homeomorphism. So he gave the following conjecture. So saying that this rho t dot is injective. So conjecture 1.7. So this is also due to Balmer. So he actually gave this conjecture in his ICM invited lecture. So ICM held in 2010. So rho t dot is at least locally injective if T is algebraic enough. I mean, if T is an algebraic triangulated category. Here, algebraic triangular category is by definition the stable category of exact Frobenius category. So if T is such a triangular category, rho t dot is should be local injective. So I didn't say that. So this map is this map is often surjective. So I don't remember the condition that, but so rho t dot is often surjective. So once, so the injectivity is very, I think, difficult. But if if T is an algebraic triangle, the category rho t dot should be injective. Okay. So I will also speak about this conjecture for our tensor triangle category D minus small mod R in maybe section 3. So from now on, let me introduce some notation. Let me fix some notation. So which will be used throughout the rest of these talks. So notation. So first, R is always commutative Noetherian ring. R is always a commutative Noetherian ring. And mod R denotes the category of finitely generated R modules. And proj R denotes the full subcategory. By the way, all subcategories appearing in these lectures are full, assumed to be full. So the full subcategory of mod R consisting of projective modules. And so D star R denotes the derived category of small mod R, yes, where star only moves. So star is either minus or B. B denotes the bound. B denotes bounded. So D minus R denotes D minus small mod R, and DBR denotes D big mod R. And we also use K star R to stand for K star proj R, not mod R. Okay, K star R is always a homotopy category with projective R modules. Okay, so finally, we end this section by let me end this section by explaining how difficult our D minus small mod R is. So actually, from the next section, we will study the tensor triangle, fixed tensor ideas of D minus small mod R, so D minus small mod R, and the Balmer spectrum of this. So, but there are many difficulties. So let me explain about them. Explain them, the difficulties. D minus R. So actually this is a tensor triangle category, but there are many problems about this. So first, D minus R does not have arbitrary direct sums or direct product, because we only consider the finitely generated modulus here, so we cannot take freely the direct sums or infinite direct sum or infinite direct product. But sometimes we can take this. So sometimes, even in this triangle category, we can take infinite direct sums sometimes. And actually, somehow, this will play an essential role in our proofs of theorems. So I will explain this later. And so this is the first difficulty. And second, d minus r is not closed under duals, any duals, like dual by base field. Indeed, we only consider the right-bounded complexes here, so we cannot take duals. And in particular, d minus r is never rigid. So here, what is rigid? So in tensor triangle, the category is called rigid if the following condition is satisfied. So T is, so a tensor triangle is the category T, it's called rigid. If there is some factor D from T to, so this is contravariant factor, exact factor, and there is an isomorphism, factorial isomorphism on T, A tensor BC, and on P, A, BB, tensor C. So, but we don't have such factor D for D minus R. So d minus r is never rigid. So, and I think there are quite a few results on rigid tensor triangle categories in the literature, but we cannot use them. So, moreover, d minus r is never closed as a symmetric monoidal category. And finally, the thick closure of the unit R is not equal to d minus r. Actually, the left-hand side is equal to kdr. So the bounded homotopy category of projective modules. So this is not equal to d minus r. And again, it seems that there are several results on tensor triangle category whose such that the thick closure of the unit is equal to the whole stuff, whole category, but we cannot again we cannot use them. So there are several such difficulties for our d minus r. So, but still we have several results on general tensor triangle categories, there are some results which are available for our d minus r, so we will use them from the next section. Okay. Still, I have 5 minutes, but maybe I should stop here because this is the end of the first section.
To the many analogies, can you hear me? Can you hear me?
Yes, now.
So with respect to the many analogies that you drew between the Balmer spectrum and the classical spectrum, I was just wondering if there is anything known about the cruel dimension of the tensor.
Cruel dimension?
Yes.
Of the Balmer spectrum?
That's right.
Yeah, indeed. So even in the case of discrete variation rings, it is not finite. So we will show this if I have time. So at the end of this lecture. So yeah.
So you're saying that it's always infinite, or
Yeah, if the ring is at least when the ring is discrete variation ring, any, so always it is anything. So that's kind of sad for me.
Any further questions?
(1.6).
If the scheme
Yes.
would be
Yes. Yes.
perfect,
Yeah.
that means that all categories, categories, this is what I said.
But in general, if you ignore the tensor, the monoidal structure, it is not true. So there are many derived equivalences over algebraic variables. So this isomorphism is also has information on tensor structure. So this is kind of essential in this theorem. Is it your answer?
Yeah. There is no conjecture it doesn't include would be open self-confined spectrum.
I see. Yeah.
This is somehow
Mm.
an indication.
Yeah. Yes. Even in the smooth case. Mm.
To use the tensor.
Yes. This is the point.
There are no further questions. We are almost done for the day. We have one more event in the day, which is a welcome reception at the Genesee Grand Hotel at 7 o'clock, which is pretty soon. So let's thank the speaker one more time and all of today's